Hello, today I will show you something visual again with a formula that I have seen on Quora. It's written on the cube. This is a cube you see here, and yeah, it's a little box. Next to it, it's a triangular pyramid that I made with folding an envelope and cutting a flat base. Right. Those two objects, a cube and such a pyramid, or maybe other objects like a prism, those objects are called in English polyhedrons. Polyhedrons are space objects that are formed by bringing together polygon faces that can be regular faces like from a cube, but you can have irregular measures, so that you get something rather weird sometimes. You can create rather complex structures, and there can be many faces. If you have small faces, you will have many possible connections. If you have large faces, you will have less faces. Okay, you have to turn around in space and bring all faces together. Okay, well, what does the F plus V minus E mean? I will show it on a cube because it will be easy to do that. The F stands for the number of faces, and I wrote it down here for the cube. You have 6 faces on the cube. You can easily check that for yourself. I don't have to explain that. The V stands for vertices, and vertices are the corner points that you have on such an object. On a cube you will have 4 corners on the top and 4 corners on the bottom. So that's 8. And the E stands for the number of edges. You could say that the edges are the lines that connect the corner points, and they are the borders of faces. And you have 12 edges on a cube. You can check that for yourself as well. I don't have to explain that. Let's work that out. 6 plus 8 minus 12, that's 14 minus 12 is equal to 2. Right. But on Quora they mentioned that this equation and this identity F plus V minus E equals 2 will hold for any polyhedron, any regular or any irregular polyhedron. And of course you could say I will check it for some other object. Well, let's do that for the triangular pyramid. Right. How many faces? 4 faces. Yeah. Check that for yourself. It's easy to see. You have 4 vertices and you have 6 edges. 4 plus 4 minus 6 equals 2. It holds also for a triangular pyramid. Well. But that's now interesting. We could create more complex things, but we would have to cut paper for a long time and try to build irregular objects, which is not that easy to do. I eventually came up with other ideas, like bending copper wire. I will show you such a thing later on. But I was struggling to have a simple explanation that it would hold for any possible construction of a polyhedron. Because how can you tackle the general case and say that formula will still be general? Right. Okay, let's put those objects away. And let's come up with a paper that will show you the development of a cube. If you understand the development of a cube and how it is built face by face, then it will become more clear how it could lead to the insight for the general case. Okay. I have 6 faces, so the F1 is the first one, the F2 and the F3 are the side faces of that one. The F4 is another side face, but it is also a side face for F2 and F3. And then F5 is the last but one, and it will be linked also partly it will be linked to this one and the other side faces. It will be linked to three other faces, and the F6 will be the last one, and it will be connected with 4 other faces. And I wrote down the number of V's and the number of E's on each face as I built the total object. And I said, okay, on the F1 I can write 4 V's in the corners and 4 E's for the sides, for the edges. I hope I believe you understand that I can do that, because I'm still starting from scratch there. And then I said, well, I add the F2. Will I add the same number of vertices and edges? No, not. I won't, because I don't have to add an E here, and I don't have to add the V's there in the corners, because those V's and that E is already showing up on F1, and it's a joined edge, so and joined vertices. We will add 3 edges and 2 vertices, because we don't need extra vertices to connect to the face that I started with. What's the conclusion of that? You have one more edge. Yeah, I will say on the F1, you could say that the delta E is equal to the delta V. The delta, I say delta because we have to total the deltas to get to the total vertices at the end of the construction. So delta E equals delta V on the first phase, but on the second phase the delta E will be one more than the delta V. Okay, and on the F3 we have a similar scenario. Okay, on the F4 I had started writing the E's here and the V's there, but I couldn't do that because that E is linked to that E, so it hasn't an extra edge that adds up to a 4. So it's the only edge that is left to add is this one, which links to F5. And you could still say that the delta E equals the delta V plus 1, but because the delta V is 0 and the delta E is 1 there. So it holds for F2, F3 and F4 that the delta E is the delta V plus 1. On the F5 we have the same scenario as for the F4. There's only one edge that will add to it. And on the F6 we don't have to add anything at all except the face itself. So there is no extra E or no extra V to add. You have to cover up an open box. That's it. I wrote it down in formulas. So for the F1, I said the delta V equals delta E, and that's the value of 4 in the case of a cube. But it could be another value in case of another polygon. If you have a pentagon, it would be a 5. If it's a hexagon, it would be a 6. But you can have more than that, or eventually less. It could be a triangle. It could be 3. On the F2 until the F5, so the second until the last but one, you will always have that the delta V equals the delta E minus 1. And you can check that for any situation. And it is easy to understand because you don't have to add two vertices. There are two vertices at least that are missing, because you have to connect to two vertices, and there are this one edge that will be less. Okay. So check it for yourself if you don't believe it. It is always true, always, for any situation. And for the last one, the delta V will be equal to the delta E, and it will be 0, because it's only the F value that will change. The delta F is always 1 in all of the cases that you build an extra phase, of course. Let's add it up. The sum of the delta V is called the V, the total V of the constructed polyhedron. The sum of the delta E's will add up to the E value. And you have the minus 1 that is added F times minus 2, because in the first and last one you don't have to add it. So the minus 1 will add up to F minus 2. Okay? With a negative sign, because it's negative 1, so it will be a negative F minus 2. And if you rearrange that identity, you will come to what I had said at first, with the two isolated on the right hand side of the expression. F plus V minus E equals 2. Okay. I worked out a little situation for a triangular prism, so I said that was the F1, and for the F1, yes, you have the 3 edges and the 3 vertices, so the delta V minus delta E equals 0. For the F2, you have to link an edge, a vertex, and an edge. Okay, the delta V is delta E minus 1, or delta V minus delta E is minus 1, and like as I write it here. And for the F3, it will be the same as for the F2, and for the F4, you don't need extra edges, you don't need extra vertices, so of course both values will be 0, so the difference of them will be 0 as well. And if you add it up, V minus E equals minus F minus 2 between brackets, I pointed to the left hand side, because I hadn't space anymore. F plus V minus E equals 2. work it out, but you will understand it is a general identity. They said that Euler hadn't proved it, and I think it has been proved here, which I don't know if Euler hadn't proved it. I'm not sure. Huh? Okay, but right. Let's show you something else. Yeah, something visual again. Okay, I constructed different objects or parts of different objects. I said the starting polygon could be bended from copper wire. Right. And here I show you a polygon in space. I call that a space polygon because it isn't able. You could put it on a flat face. And it is a polygon because, of course, you have an equal number of edges and vertices. The vertices are a bit rounded because copper wire like that is not easy to bend neatly in corners, straight corners. But you have the base of a triangular pyramid. The only thing you can add to it is here an extra edge and there an extra edge. And yeah, between vertices that are not interconnected. And you will see that you can put the faces on it afterwards. So you can construct with copper wire the number of vertices you need, and yeah, the starting polygon to work it out to construct a final object. And yeah, here you see the base polygon for a cube, right? It is also polygon because it has yeah, linked all vertices by lines, by edges. Okay, and you have to add, of course, edges to it to put faces on the surroundings later. And here I show you some yeah, general stuff. It is not regular. And I said, okay, you can bend a starting polygon and put other polygons on that base polygon. You have to link vertices. And yeah, you will also create a general thing that you have to complete with extra edges. And I said at a certain moment you could consider a rounded face instead of a flat face, and it would still hold. The formula would still hold if you accept rounded faces, because you don't add extra edges at that time. If you have to consider flat faces, sometimes you have to add an extra edge, because you can't say that all points are collinear. 3 points, yeah, in space are no, coplanar. 3 points in space are guaranteed to be coplanar, but if you have more, then you should cut the structure with an extra edge, but it will lead to an extra face to add. And it can be different times that you have to add an extra face, but each time you add an extra edge to complete it, to make it possible. But you can construct a copper wire structure that has all the vertices you need, a base structure. Right. So you see that I have done some effort to make things a bit clear in different ways. Okay. It's up to you to be interested for yourself. But I will end the presentation here because otherwise it would be too long. See you next time.